All right, so welcome to Warsaw.ai, our first episode, first ever. My name is Przemysław, and I have a few partners in crime. So Marcin Cycoń, where's Mark? Paweł and Tomek. So if you have comments or questions, or you want to blame somebody, this is us for organizing this thing. We had an idea to do something for a long time. We started discussions earlier this year with Paweł, probably in March. We wanted to do something before holidays, but it's really hard to get an event like this together. So if you want to help with this at some point, you're more than welcome. I want to start with a kind of personal anecdote in the beginning. So, I worked at Google for a long time, and Jeff Dean started talking about AI changing the world, and we're listening. And then he started writing TensorFlow. The whole Google was listening. Then they bought DeepMind, and it was like, wow, that's a nice company. The whole Atari thing is amazing. But it wasn't really touching me in any way. I was looking, and it didn't trigger anything. But then I read a paper from Google Brain, which was called hand-eye coordination. They took these 14 robots, set them in front of these little gray trays, dropped everyday items into these trays, and initially randomly set these robots to try to pick something from the tray, completely random. And then they were training neural network on top of this data. They collected like 800,000 examples over 4 months, dozens of the robots running there. And this network was successful in picking 30 items in 31 attempts. Without any prior knowledge, right? When we started with, and then I thought, okay, this is going to change the world. This is really something that I learned to spend more time on. We started a company based on this idea, and today robots are picking stuff. So that's kind of my personal story on why I think it's such an important topic. So when we were starting this event, we wrote a little manifesto why we're doing this. And there are kind of three things. One is that AI is going to transform the world. The second is that we're going to solve problems that were not possible to solve, with computer science before. And then that we're going to reach superhuman capabilities with this software. So, this is what at least the organizers believed in. And I would like to do a vote of hands. What do you think? Is it possible that we're going to reach these three things? If you think so, raise your hand. Okay, not bad. At least half of you believe that we're going to change the world. So this is really, one of the reasons why we do this, because we want to build a community of people who are interested in the technology and believe in some things align around this. So one thing is, in our goals is integrating community in Warsaw, but maybe in Poland as well. Focus on technology and not hype, so really talk about solutions and how people build their products and build their systems. Offer advanced education, and in this case, the education is kind of overloaded word because we don't want to have very long lectures and things that you can find in other places in the internet, schools, but we want to offer education by getting practitioners together and having a discussion about the, not papers or not only papers, but things that we have done in the product space. So, these assumptions, they also mean that organizing this event, we kind of filter participants. So we try to make sure that people who are interested in technology come here, and recruiters, sales, and marketing people don't waste our time. So with this, since we're talking about the community, so I wanted to ask a few questions. So have you used tools that we use in deep learning, like TensorFlow, Keras? Okay, this is really good. Do you understand theory behind it, or maybe do original research? Okay, a lot. Have you built a product using machine learning, or you're in the process of building a product? Woohoo! Everybody! This is fantastic. Okay, so I think we've achieved our goal of getting people together, so now I'll accelerate. Our plans are to have more than one. It's episode 1, right? We would like to do something like 4 events a year. This is a lot of work. We'll try to do this on Thursdays, so please move your swimming pool. Once a quarter, you'll come here, hopefully. Each evening we'll have 3 or 4 speakers, short talks, something like 20 minutes, some Q&A. Lots of time for networking and this advanced education afterwards. We're going to provide some snacks and drinks. This is thanks to a sponsor. And with this, I also have questions for the show of hands. Do you think that alcohol in this event is acceptable? We don't have an alcohol today, so no worries. Do you think that alcohol in this event is necessary? Okay, only 4 votes for necessary, but everybody thinks it's necessary. Very good. So today, we have these drinks and food thanks to sponsors. We're also recording this thanks to sponsors. Today, NVIDIA is our sponsor, and Przemek will have a talk in a second. And we hope that it's not a recruitment event. He's going to show you what he does. You're free to talk to him, but there's not going to be like a big poster, what are open positions. And we hope to do it the same with other sponsors whom we need so that we have something to do. Okay, with this, I'm going to turn over to Paweł, who's going to run the event today, and let's start.
Okay, thanks Kasper for the introduction. Okay, so without further ado, let's start our first presentation. Przemysław Strzelczyk, representative of our sponsor, NVIDIA. Okay, Przemek, floor is yours.
Thank you very much. Okay, so my name is Przemysław Strzelczyk. I'm the deep learning manager in NVIDIA, and I'm leading the team deep learning algorithms here in Poland. Today, I would like to tell you a little bit about one of the projects in our team. I think it may interest you a lot. Topic is mysterious cooking, but I will explain in a few words what I mean by that. So, if you would like to prepare a delicious meal, what would we need? So, first of all, we need to have some experience with cooking, with preparing meals. Of course, we should have a good quality ingredients, some kitchenware, well-equipped kitchen with all the tools and devices. And of course, last but not least, a good recipe, proven recipe for our meal. And when we pull all this together, probably we'll be able to prepare something delicious. So by analogy, we can think about what we need to train a neural network. So first of all, we need some experience, like this guy, the first one. But this is not enough. We need to have good quality data. So, like, here we have the ImageNet. And we can start, but to reach this state of art, we need to have good equipment on which we can train our neural networks. Here we have the DGX1. This is one of the servers that NVIDIA produces with 8 GPUs inside all the time, which is a good node in the cluster. But to really have the joy of training neural networks, we would like to have good recipes how to train these neural networks. We have scripts that are stable, that are proven, that work with the frameworks, and the piece of software, the software stack that don't have problems with setup, with configuration, compatibility, and so on and so on. So we would like to land somewhere there, so we better than the existing. Here's an example from the object, from the image classification. Yeah, so what can we do about this? So I mentioned a little bit about the problems we have usually when trying deep learning, trying to train neural networks. So first of all, we read a paper and we try to reproduce it. So we see, oh, there's a new brilliant result. We are looking for the GitHub if there are samples. No, there are no samples, so we try to implement it our ways. Usually we end up with something which does not reach the accuracy or does not train at all. Usually the problem is, there are many problems why this happens. First of all, the authors are pushed to publish very quickly. So they don't have time to test everything. And sometimes they publish in a way that they do not say about details, about these real details which makes it work. So if you want to reproduce, usually you have to guess how was this, how this can work. So the other thing is that I mentioned before. So this is a research work. So it's a research code. So usually it's far away from good software engineering practices. So generally, if you want to put it on multi-GPU, multi-node, and make some adaptation, optimization, forget about it, you will spend weeks. Additionally, you can encounter problems with setting up the environment. Like you have the workstation, you put it inside the GPUs, CUDA drivers, and then install framework, and you have the different compatibility issues. The framework changes a lot. So yes, you spend a lot of time making this this kind of work, which is not a data scientist work. And when you finally get your code working, usually this training takes too much time. So you put your training for 2 weeks or let's say a week, and then in the middle of the week you just check that, oh, there was a bug in the code and this didn't work. So you have to cancel and start again. So time matters here. And the last, I mentioned it before, it's the compatibility issues. So frameworks changes. Today you have variable, tomorrow you have tensor, and maybe the day after tomorrow we have something else. If someone's programming in Python, they know what I mean. So the frameworks changed, so your script had to change. So, and yeah, we are trying to make our scripts working with the different releases of frameworks, and we encounter this very frequently. So, what is our solution? Our solution is that we would like to deliver proven training recipes to accelerate the research and applications. So NVIDIA wants to prepare a bunch of scripts with model, with the recipes, with the training scripts, parent scripts, so it makes it easy to start with deep learning. And additionally, because we have the access to clusters of GPUs, like I mentioned before, about the DGX1 station, so we have plenty of them, and we can make experiments. We can test our hypothesis, and therefore we can share the best neural network training practices. So we can take the paper, check if what is in the paper is true or not. If this author was lucky, or it is more knowledge in that. And of course, last but not least, we want to show the potential of GPU-based deep learning, especially show some hardware improvements we have in our GPUs. so they can be applied in deep learning. As an example, Volta Tensor cores. Of course, we also promote our architectures, GPU architectures, and whole the software ecosystem for NVIDIA for deep learning. So here is our workflow, how we work by preparing those recipes, those scripts. So first of all, we start with model selection. This is something we do when we're talking with our clients. So we're asking them, what do you need? What the people are interested in? Which models we should select? Which model will be most beneficial for everybody? So we make this model selection, and then we try to make a kind of initial research, check what are the options. For example, we can talk about the Resident 15. I think everybody heard about the Resident 15. Do you know there are many versions of Resident 15? No, I'm not talking about different length of resonance. So the one in the paper, the one which was, let's say, had blocks switched, random, rational, and convolution, and the one which is really implemented. So the one which is in the paper and the one which is implemented in many frameworks are two different models. And just there was a example of misunderstanding about when on one of the blogs there was a comparison of Google TPU Resident 15 version and Google and NVIDIA GPU Resident 15 version, and they found they compare apples to oranges because there were different models underneath, both named Resident 15. But okay, I'm going to the details, but I want to go further. So generally we start with observing what's available. If there is a major implementation somewhere on GitHub, this is our base. If not, we start from scratch. And we make it running, and then we quickly adapt it for the mixed precision and multi-GPU. We are interested in speed up with reduced precision computations, and we are interested in multi-GPU and in future multi-node. First goal is to get the accuracy in 6 configurations. So we have FP32, so floats, and FP16, so half floats, for 1, 4, and 8 GPUs. And if we are able to make it converge for those platforms, then we go further. Then we run additional checks, because if we were able to reach the accuracy for the run starting from one random seed, is it enough? No. We have to check from different random seeds. We have to check how the model behaves if we start from different conditions. So we can really prove that these scripts are stable and that this model trains in a stable way, and get to the accuracy with given probability. Then afterwards we switch to performance tuning. So because NVIDIA is a performance company, so we want to optimize everything. So we will make the optimization both on the level of algorithmic level and hardware level, library level. And then there comes the usual software engineering stuff. So we write regression tests because we would like our scripts to work with new version of frameworks. So we would like we don't want this to be our scripts to fail when new framework version is published. Then we prepare documentation manuals, tutorials how to do and publishing on GitHub and in containers. So how it is called with the NVIDIA deep learning ecosystem? So this is a kind of overview of what we have. So for the accelerated deep learning, we have, probably you know, we have high performance computing libraries like QSparse, QGlass, QFT, and we have deep learning specific libraries like QDNN for computational neural networks and NICL, which is used for multi-GPU computing. Then we have containers. So NVIDIA is trying to release a stable CUDA libraries plus frameworks in a container. So you can just start to work by downloading container, a Docker container, and everything is configured inside and it's working. So you don't have to take care about how these things work together, about the compatibility of different things. Last but not least, okay, we have now containers for the TensorFlow, PyTorch, and Mixing. Last but not least, we have a cloud, and NVIDIA is developing the cloud, but today I will not talk about it. So I mentioned about the multi-GPU platform. So this is a one node of this on which we are making our experiments. It's with 8 GPUs. This is DGX1. We have also DGX2, which is with 16 GPUs, a little bit different architecture. Here you can see that you have CPUs that you have approximately 5 cores per one GPU, and the GPUs are connected both by PCI Express and by NVLink. This is a special bus, like a kind of token ring, as you see, which connects the GPUs so they can exchange the updates during training very quickly. And yes, and I mentioned about the FP16 mixed precision. So we know that you can train your network with reduced precision, and you can go to FP16 without significant problems. So you have to take care about that you are reducing the range from 8 bits to 5 bits, and reduce the precision. So the problem is that when you train mixed precision or FP16 precision networks, you have to make some loss scaling because the losses during training is becoming very small, and it goes out of the range of the representation of the health loss. So there is a special algorithm for either dynamic or static loss scaling, which multiply the loss during the bug propagation and then divide it during the update. And one thing which we would like to mention is that not all operations are FP16. So, for example, if you make the accumulation, you have a batch norm like even 2K, and you have to accumulate gradients. So if they are all FP16, if you accumulate it, so you cannot fit it in FP16. So you have to make some actions in FP32. So this is why we call it a mixed precision. So sometimes you make the operation FP16, sometimes you make it in FP32. And as a matter of fact, you have some, let's say, the blacklist, whitelist, graylist. Blacklist are operations which should be done in FP32. So you convert to FP32, make the operation FP32, and then convert it back. In whitelist, it is safe to use the FP16 for the operation, and graylist is that some part of the operation of FP16, some part of FP32. And usually this is easily implemented. Here is an example. We have something called Apex. This is in PyTorch. This is a tool for PyTorch, in which we have 2 ways to implement the FP16 mixed precision training. One is to use the AMP, so initialize the AMP, and then only change 3 lines of, together 5 lines of code. And you can see that you have the loss scaling here included. And the things I mentioned about the whitelist, blacklist, and graylist, it's only to the inside. So the EMP, which is short for automatic mixed precision, knows about which layers, which operations can be done in FP16 and which should be done in FP32. So it's automatically. The other approach is FP16 optimizer. So we have a special optimizer implemented. This is the other way of doing it. The optimizer implements also the dynamic loss scaling. Dynamic loss scaling tries to adapt this scaling factor during training, but it has some drawbacks. Maybe we'll discuss it later if you want. So I told you also about the run-to-run variance. We are checking how the model changes if we start from different random seeds, and we are also checking how the model changes if we start from the same random seeds. Because in a parallel distributed world, there is no guarantee for the operations. So you have an example. It depends how you sum up these 3 things. You can get different results, and this is all about the order of summation. So you can encounter those problems. Actually, this variance is not very high because it somehow is hidden. The problem is with the other variants, when you start from the different seeds and you get different results. So we are making those tests, and usually when the variance of the results is high, we have some problems, usually with data loading, data preprocessing, but sometimes we have some silent fails inside. So those are really hard to track. But before we publish the model, we want to check. And as a matter of fact, because, for example, one of my engineers was training ResNet 15 for 400 times, so we are able to find really the situation which normal user would not encounter. So this is why I said we are trying to deliver proven recipes. So we double check it or triple check it. Of course, we publish the best model because during these runs we have different models. We can even assess what is the probability of reaching a certain accuracy. Then comes the performance. So generally we have something we call the speed of light. Speed of light is a theoretical limit of the performance we can get. Of course, it's top secret, and I will not reveal it for the different models. Other performance measures are time to train, which could include validation checkpointing. We measure items per second. We measure what is the speed up between FP16 and FP32. And we also measure the with GPU scale. So we set the batch size per GPU is fixed, and we increase the number of GPUs. You can see the results for the ResNet 15. This is from our GitHub repository. And one thing I mentioned to you about the Volta cores, the tensor cores. So it's a specialized unit which can compute the matrix, multiply and accumulate on FP16 or FP32. So it multiplies by FP16 and the results FP16 and FP32, and it can increase the speed 8 times even. So this is why we are investing so much in FP16, because it is supported by Volta and it can really increase. Of course, usually you don't have 8 times increase because there are many other issues, but this is why we have some. One thing we also want to mention is that we are working, not my team personally, but there is another team in NVIDIA, also in Poland, which is working on NVIDIA data loading library. So we figure out there is a problem with CPU preparing data. So CPU is preparing data, making a documentation and putting on the GPU, and GPU is waiting. So we have a time when GPU is idle and the CPU is making computations. So there was an issue. There was an idea to put some computation like augmentation and decoding, like JPEG decoding, onto the GPU. So and this is why we have this project, and this is currently under development. There is a release for image classification. Now we will do for segmentation also and detection. We also, because we are trying to reach the target accuracy or get beyond the target accuracy from the paper and shorten the number of epochs to train and shorten the time to train, we are experimenting with different things which are in the papers. I mentioned to you that we are analyzing what is in the papers and testing the hypothesis. So like, for example, you have some examples like label smoothing, which is working, with decay instead of to normalization for SGD with momentum, and many others. I think I can talk about it more. Actually, I can talk a lot about it afterwards, if you want. Currently, our pipeline is that we released this project started this year. So we released the GNMT with the 4-layer reduced layer and ResNet for the PyTorch. We are releasing ResNet for the MX and TensorFlow in the future, and for the detection SSD. And there are some models for text-to-speech, machine translation, segmentation, imaging, medical imaging, but I will not say which exact models are there. So to summarize, we deliver some sources which are packed also in containers with the training inference benchmark scripts with best practices included, which are optimized for GPUs, our GPUs. Also with the performance and accuracy results, you can go on this, check the README files, you can see the results. With the manuals documentation, describing the model methodology we use, and in the future we'll also publish the pre-trained models for that. And that's all, thank you very much.
Thank you very much, Przemek. Are there any questions, Przemek?
You mentioned that sometimes you have quite big variance in some cases for some models. And what was the reason of this variance? Can you give some examples?
Usually it was something with data. Usually there was something with data loading, data preparation, data processing, like skipped batches or some errors during the forming the batches, and then it influenced the results of training. So mainly data preparation. There were some things which I call the silent fails, like for example, if you use the loss scaling, you amplify the loss, but you can go out of the bound, so you can get the infinity. And sometimes this infinity is treated in a certain way. Actually, I think there's a disclaimer on the QDMN now, and this could lead to some silent fails. So there are some like masks inside. Some neurons are not working, but this is due to wrong setting of parameters. Like if you set the loss scaling too high for FP16. But usually it's something with data, with the data loading and the data processing.
One more question, David?
Actually, I need it. That might be out of the box question, but do you plan similar exercise for also GPUs-based methods like XGBoost or LiveGPM?
Correct. So correct. My team is not working on other things than the deep learning and neural networks. So with the other things, we have the high performance libraries team here in Poland. But the other things you are talking about, so the other algorithms which are not strictly neural network algorithms, are not developed here. So I haven't heard about an initiative like that. Maybe there is something in US, but I have to double check this.
So yeah, let's thank Przemek once again. We'll have some questions. Okay. And now we have our guest from Krakow, Rafał Cycoń from Poland. So we are Warsaw.ai, but we invite also guests and speakers from other cities and also from other countries. In the future, maybe from other planets and or other universes. So today, Rafał arrived from Poland. It's not that far, and he will tell us about one-shot learning. So learning from a few examples. Okay, can you start?
Hello everyone. I'm CTO of the Formas company, which was a machine learning consulting company since 2013. I said was because quite recently we, after a quite successful project for a Singaporean corporation, we converted our company into a product company that's called Shotbots. And what we do is basically we employ detection and segmentation methods, of course, all based on deep learning, to detect products on shelves, to see them on the picture and identify which product they are. We are able to identify like thousands of different products. And one of the biggest problems that we have encountered, which is also very, very common in deep learning, and I think it's actually one of the biggest limitations of learning, is the necessity of having a lot of training examples for the deep learning to work quite accurately. This is an image, I believe it's from the Carpathis course on deep learning, and I really love that image. You can see how our brains work, and how deep neural nets fail at such simple examples. For us as humans, for example, we know immediately that these things in the bottom right corner, they are chairs. Despite the fact that they are all very, very different, we know that we can sit on them, okay? If we show a picture of an elephant to a child, that child can immediately identify other elephants on the TV, in a zoo, or if you show it a stuffed elephant, the child will tell you it's an elephant. As a single example, is very often all that is needed. For deep learning, to identify, for example, these chairs, it will need like probably thousands of pictures from different viewpoints, different illuminations, and blah, 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 blah. And this is especially important in cases when we are operating in data-poor applications, like for example in medicine. But anyway, what can we do when we are facing, when we don't have enough data? Of course, we can employ data augmentation, which also, because we are presenting them all of different images or other types of data in a lot of different forms, it generalizes better. And it's a very simple idea. We can do heavy regularization, but it helps us with overfitting, because if we don't have enough data, our models obviously tend to overfit a lot. We can tackle the regularization, but it still won't help us much. We can of course use pre-training, or we can use semi-supervised learning. But there are several other techniques and several other new approaches that are trying to solve the problem of deep learning needing a lot of examples. Like for example, synthetic data. I like the coincidence that Kasper started with the anecdote on the Google Brain project, because as you saw, Google Brain, they ran the experiment for 4 months, right? On a lot of robots to collect data, to then train the neural nets on them. And this is the approach employed by OpenAI. Probably you have heard about this. They run a lot of simulations. This is the Mohojko, I don't know how it's spelled, sorry. This is the physics engine, which is able to simulate every movement of a robotic hand. And you can see that they run a lot of simulations with very different background colors and very different colors of joints to like randomize and provide a lot of variety in the simulations. And on the basis of only the simulations, as far as I remember, they were able to train a model which was able to manipulate this cube and rotate it and pivot it and so on and so forth. It's a very nice application. I really encourage you to have a look at the link. By the way, this is from a very recent paper. It's from the Big Guns or something like that, and the results are really incredible. You can see these are the artificially generated images of resolution 512 by 512. I think it's the first generative accelerometer that was able to produce such convincing results. And maybe it opens door to very advanced data augmentation, or for generating new data on the basis of unsupervised, unlabeled data that we already have. And this is an example of an application of GANs. These are here not the big GANs where I showed you just before, but so-called recurrent conditional GANs. To be honest with you, I have no idea what it is. I mean, there are a lot of GANs, but what I really like about this is that they used GANs in a medical project to generate time series data, and they augmented the original data with the artificial data to improve the model. And as you probably well know, the AlphaGo Zero project by DeepMind, it was able to surpass the AlphaGo version which bet the world champion, and it did so only by self-play. So no data, no external data from human players was here, and it did so in a really quick after not training. Okay, and one of the quite interesting approaches to handling situations when you don't have a lot of data is the so-called one-shot learning paradigm. You can see on the bottom, how does it work? Let's say you have here. Here you can have, so-called your memory bank, right? So you have 3 classes here, and these are all the training examples that you have. And a new object arrives, a new image, and you try to classify this image. This is called the one-shot learning because you have only 1 example per class. If you had like 5 examples, this would be called function learning and so on and so forth. And this is how the model works, but it is very often trained in the so-called verification manner. So basically, you show the model two objects from the same class, and you train it as, okay, you have to know that this is the same class. Then you show 2 different objects, and you see these are different objects, okay? And you go like this for a long time, and you hope that your model will grasp the idea of similarity between the 2 images that you show to it. One of the earliest, I think, applications of such an approach, it was signature verification, right? We have here you have 2 signatures, and it's a paper from 1994, as you can see, it's quite old. We have 2 signatures, and we want to tell whether these signatures were done by the same person, right? And this is done by employing the so-called Siamese network. So we have here 2 networks that are twins, right? They share parameters, they are the same networks, and we run a set of features through the network. So after all, we obtain a high-dimensional representation of the input data. And at the final layer, or at the final step of processing, let's say, we compare these two representations of 2 images to tell whether they are close enough that we can call them that they are the same, or if they are distant, we say that they are not the same. Okay, this is an example of application of Siamese networks to one-shot learning, one-shot image recognition from 2015. And you can see here, this P here is this one, so it's in the final layer. We are basically computing a difference, a distance between the representations from these 2 fields. And as I said before, the way we are training it is that we show it 2 images of the same class, and we call it, like, for example, the y equals 1. So we are providing the signal this is the same class. We are showing it 2 different classes, and we are providing negative signal. Yeah, the gradient is additive across twins. Actually, Tomasz Chiński is an expert in Siamese networks, so I believe he should be able to tell you much more about this after my talk. But anyway, let's move on. The benchmarking platform for it's called, of course, it's not official, but it's very often used. It's the so-called omnigle dataset. It's often called the inverse NIST, right? Because in NIST you have 10 digits, and you have a lot of examples of each. Here you have a lot of different symbols, because these symbols are symbols from different alphabets, and we have only a few examples of each. So it is a perfect data set to benchmark our one-shot learning. For example, we can see here Hebrew, some Bengali, and this is how a 20-way one-shot task looks like. We have this new symbol. This is our memory bank, and we try to say to each class this new symbol belongs to. Okay. And these are the benchmarks from the Siamese network. We can see here the human performance on this. This is the convolutional Siamese net. It's 3.5 percentage points below humans. This is the hierarchical Bayesian program learning. I didn't read about this, but I know that they use some additional features that incorporate the human stroke data, so the way that humans draw the symbols, so it's again a little bit. But anyway, so it got close to human performance. But what's really nice is there are some papers already, some methods that actually surpass humans in this test. And one of them is the attentive recurrent comparator, which was motivated by the way humans try to compare two images, right? When we have two images or two symbols, like for example here, we look at the first one, then we look at the other one, we look for similarities, and we switch our focus from one to the other. After we see several times, till we see that we are certain that this is the same symbol or not. This is how it works. We have here the so-called controller running on it, and it provides us with the parameters for the so-called glimpse. So for the region in the image on which we should focus on. Okay, these are the parameters. We are taking a glimpse, so basically we are extracting a touch from the image. We are running it through some feature extractor, or this is an attention here. We update the controller, and then we attend the second image. And the idea here is that we switch iteratively between the two images. Authors have tried to attend to both images at the same time, and several they tried some several other ideas, but this worked best. Of course, we are in the deep learning world, so there is no theoretical verification that this is a good idea or the best idea, but it gave better results, so yeah, so we are sticking with this. Okay. Actually, this was supposed to be a GIF, but sorry for that. You can check it out when you type attentive recurrent comparator in Google. It's really nice because it shows how the model takes these different glimpses on the symbols. But anyway, the idea of taking a glimpse of focusing on a part of an image is it's very clever, I think. It originates from the so-called draw model. It works like that we are trying to produce some parameters that allow us to focus on certain part of an image. This is, for example, the output from the recurrent controller, and we kind of unpack this output into the center of our focus area and the spread of our focus. For example, here you can see the different zoom-ins, different regions, and different spreads. Here you can see local rates because we want this. What we are trying to do is we are trying to at each single point here. This is the center of a Gaussian or any other filter. So what we are trying to do is we are trying to put these centers on different points of the image. We are applying Gaussians here, so we are doing multiplication with a series of Gaussians, and after all we are getting this. So, sorry for this. So these are the parameters of the Gaussians. We can see these are the parameters. These two are the center of the grid that we are trying to put on the image. As you can see, they are normalized, so we need to normalize them. This is the sigma that controls this is the sigma that controls the separations between the different points. And we are computing the Gaussians and applying them on the image, and we have the focused glimpse here. In attentive recurrent comparator, what they did was they applied Cauchy filters instead of Gaussians. As you probably know, the Cauchy filters have slightly a little bit wider tails, and they argued that it helped them with conversion, and they fought with vanishing gradient problems with it. So this is pretty much exactly the same idea. We unpack the values from we unpack the center of the grid and the spread between the point of application of the filters and the spread of the filter, and we are computing the filter banks, applying it on the image, and we have the glimpse. And you can see here that actually, which is quite interesting. This is quite interesting because authors of the attentive recurrent comparator, they run a benchmark to check how many glimpses do they need to attain satisfactory accuracy. and they arrived at 8 glimpses. But still you can see that this could be increased, but they didn't provide the results. I don't know why. And anyway, what to do? Because this example just showed you how we can do the one-shot learning for when you have 2 images. What to do if we have like the 20-shot problem, like I showed you before, that we have 20 symbols. So we can do the naive stuff. So we can apply attentive recurrent comparator per each pair of an object from our memory bank and the target object. And finally, we can compare the probabilities that are returned from the model to tell to which class this new object belongs. This is naive, and we can do better. And the idea here is they tried to input all 21 images into the recurrent neural net, but as you know, the RNNs, even LSTMs, they lose context very quickly, and 20 images was simply too much. So what they propose is to construct the very same naive approach, but then to connect these outputs via a bidirectional LSTM, so that we have a final layer that tries to look at all the differences between the different comparisons of 2 images, and finally compute the subclass to tell to which class this new object belongs to. And as you can see here are we humans, 95.5%. This is the naive attentive recurrent comparator. This is conv-arc. This is done on instead of performing these calculations on raw images. What they did was run the images through some feature extractors, and they compare with high dimensional feature space on only the outputs from some very deep layer, and they already surpassed the human performance of the stats. And when they applied the full context convolutional arcs, they even improved the result. Okay, I was about to talk also about the matching networks from the Google Brain group. I don't know, do I have time for this? Like 2 minutes or not really?
2 minutes.
Okay, thank you. So in very short, this is another approach. It's also very deeply rooted in the attention approach, and very shortly what it does is that it computes it's quite simple to the CMXC network in that way that we are trying to embed these images in high dimensional space. These G theta and F theta are some feature extractors, some deep neural nets. And after that, we are computing the cosine distance and the softmax between the target new class and the classes in our memory bank. But what they also did was the very nice trick in embedding this new target class, because it very heavily employs the attention. I mean, if you are interested, you can go through this after the presentation, so I can tell you a little bit more about the calculations here. But they embed the target image with taking into account also our memory set at the very beginning. And the way this model was trained was also very good, because they constantly rotated the classes, like the class types, so dogs, cats, building, and so on and so forth. So to truly make sure that this network learns to differentiate between, it can be applied to completely new types of classes and still perform quite well in the one-shot learning pattern. Thank you so much.
Thanks, Rafał. Questions? Okay.
So the question is how well these methods are dealing with image transformations, like squeezing, rotating, So in my understanding, for science networks, you are not doing any like augmentation, but in terms of the other methods, would it recognize, for example, the symbol if you rotate it or squeeze it a little bit?
Thanks, that's a very good question. When we train the models, we are also trying to do, especially with science, because we are trying to apply data annotation as well in the training process. And of course, these one-shot learning approaches, when you do a little bit of squeezing and rotation, they should be able to recognize it, but they are not as powerful and robust models still as typical networks which have access to a lot of data.
Okay, more questions? So have you heard about any methods that, for example, for pre-processing or somewhere in the middle of the network use stuff like spectral pooling? Because it seems like the problem here is that the images are of very high dimensionality, so this is to overfit the model. But at the same time, like spectral pooling provides low dimensional representation of an image, while quite low keeping all the details that are necessary for a human to recognize an image. So that would seem like a good idea.
I haven't heard about it, but I do agree that this is a very good idea. I think that New York University, the Jan Lekun's group was investigating something like that. I'm not really sure, and I haven't read much about this, but I think this is a very good idea.
I think we have time for one more question. Anyone is interested? No? Yes, David.
Can you share with us which method was successful in your company? Or at least a range of methods.
So I won't, but simply because we are still working on this. Okay, I can already tell you that in our application we found out that we need 100 examples to add. I mean, we have networks that are able to recognize hundreds or thousands of classes, and to add a new class we need hundreds of examples, and this can be dramatically reduced. But we are still working on this. I can't tell you much more right now, maybe in the future. Thank you so much.
Thanks, Rafał. So last but not least, our next speaker is Marcin Możejko from Sigmoidal. Yes? Yes. So the title of this talk is Uncertainty in Neural Networks. So I'm very certain that this talk will be great. Good luck, Marcin.
I also hope that. So, yes. So hi, my name is Marcin Możejko, and I'm really glad I could be here. So I'd like to thanks to organizers for organizing this fantastic event, and the presenting speakers for really interesting talks. And thank you for being here. So let me briefly introduce myself. So currently I work as Principal Deep Learning and Machine Learning Engineer at Sigmoidal, a Warsaw-based AI consulting company. My main area of expertise is natural language processing, computer vision, and as you may see here, some kind of mathematical foundations of machine learning. I also work as a researcher at the Tensor Traffic Group, where we work on different algorithms, which my name is to optimize the traffic light setups in this case. Okay, so I'd like to briefly introduce you to my goals for this presentation. So in like the next 20 minutes, I'd like to provide you 3 themes. So first theme is that I want to provide you with some kind of systematization, structurization of different kinds of uncertainties. The second thing is I like to show you simple methods, how you can estimate these different kinds of uncertainties. And the third thing is that after this presentation, which is relatively short, I'd like to show you where to go further so that you can continue on the research on your own. So first thing is that, so let me structurize, what are currently agreed, so what is the current agreement on what kinds of uncertainties our model can suffer from. So maybe I will tell you why I think this is important. So what we've noticed is that in many papers, really popular papers, the different definitions and different uncertainties are often mixed up. And it's really annoying when someone claims that that the paper presents the method that can assess whether this case is known to the model or not, and it turned out that this is actually the paper about whether this case is hard to classify or not, because of various reasons. So actually we'd like to provide you a definition of different kinds of uncertainties from relatively unknown paper, which I think did it in a really astonishing way. So this paper claims that there are 3 types of uncertainties. So let me start from something which is called the aleatory error. And the aleatory error is something to refer to also as statistical error or reducible error. So it just, in simple words, your case suffers from the aleatory error if it's really hard to classify, and it always will be. So there are different kinds, reasons for that. So for example, you may suffer from inaccurate measurements. This is really important in case of regression. So for example, if you cannot be 100% sure whether your measurement is correct, you cannot predict it properly. The second thing is the natural complexity of data. I really like to think about this example as let's call it the twins problem. If you have twins, it will be always hard to discriminate between the twins, like distinguish between twins, right? Because they are pretty similar to each other. And the last line is something what I call the insufficient discriminatory properties of data. So actually, I will show you something so I have 2 sisters. They are completely different. They look totally different, but I can show you how you can make them twins. So for example, imagine that you have only one piece of information. You have a piece of information which claims about a given person, whether this person is my sister or not. So in this case, it's for every model which you will build, it's impossible to somehow distinguish between these 2. So actually this set of features makes my sister twins, right? So if you, just to summarize all these things, the main reason behind this kind of uncertainty is that I think it's really, really nicely stated in this quote at the bottom of this slide, which claims that you can't distinguish between examples represented by the same or similar data points. And actually, I found this quotation in one really old paper, and this is the only paper which stated that this citation was originally this was originally said by Pierre-Simon de Laplace, so because it was called the Laplace rule. But I think that any reasonable person can claim that, so I will not. I think it doesn't matter so much who said it. And there is famous physical theory or physical theorem which actually is, in my opinion, strictly connected to this kind of error, and this is the Heisenberg rule. So there is now a good sign for you. So basically, on this picture, you have Werner Heisenberg and Mr. Wigner. So can anyone tell me which one of these gentlemen here is Mr. Heisenberg? I know that at least one person knows. So as you may see here, It's a hard question, right? Because who knows how Mr. Heisenberg looked like? They are pretty similar. They wear almost the same hats. And the answer is that this gentleman on the right is Mr. Heisenberg. Yeah, so this is a really nice illustration of this kind of error. Okay, as I mentioned, I'd like to provide you with a really simple computational trick, how you can measure the level of uncertainty of a given example. So there will be math here. So let's concentrate on this slide. Okay, so the trick which I will show you works for models which has the softmax output and is for the models which were trained using something which is called categorical cross-entropy. It's sometimes also referred to as Kullback-Leibler divergence or cross-entropy. It has different names. And actually, let me state a few simple facts. So first of all, when you train a model with this output, you would like to assign the highest probability, actually the probability of 1, to the true class, right? Oh, actually I have a question, because I will use the something which is called entropy. I have a question. Who here knows what entropy is? This theoretical information. Oh. Okay, so who wants me to explain what it is? Okay, so I will assume that you know what entropy is. So basically, if you think about it so if you look at this closer, if you make your network to assign the probability of 1 to a single example, what is actually doable in case of modern neural networks, then the entropy of such output distribution is really low, right? So one may assume that easy examples for which this is possible should have lower entropy. So let me show you an experiment which confirms that hypothesis. So what we did here is that actually we trained a model on endless data set, and here we trained the model on train set, then we evaluated probabilities on the test set, and here what you may see is that for the test set we computed the cases which were correctly classified, which are blue here, and misclassified, which are orange. And so here you may see so this is logarithmic density of entropies on this test set. So as you may clearly see, for the misclassified cases, this entropy is usually strictly higher. So, and if something like this holds, one may ask if we could use this metric in order to classify examples, whether they are correctly classified or not. So here you may see, so the two, first of all, ROC curve of such classification task and precision recall curve of this classification task. And if you are familiar with these metrics, you may see that this is a really, really good classifier, which confirms that if you both have high values of entropies, it's highly probable that your cases will misclassify, and you have lower values of entropies. This also, one can assume that these cases are correctly classified. Precision recall curve looks slightly worse, but remember that this simple model has 98% of accuracy, so you have only 2% of misclassified cases. So this makes this problem a little bit harder. Interesting fact, here I also showed you 5 examples with the highest entropies. So as you may see, this is, so the true class of this is 9. Okay, for me it doesn't look like 9. This also, and yet this looks like incomplete number. This one, to be honest, I don't know the reason why they were classified wrongly. Yeah. So as you may see, by simply computing the entropy of outputs of your model, you can have a really nice score for the adaptive uncertainty. The second kind of error, which I'd like to tell you about, is something which is called epistemic error. So the epistemic error comes from the lack of knowledge in our dataset about the given example. So you may think that cases which suffers from epistemic error are the cases which are not well represented in our data set, but one may assume that the more data point you get, the better your model will be on these examples. So you may think about this, that you're waiting for once you gather more data, you're actually waiting for the perfect data set, because everyone may assume that at the end of this process you will have the perfect data set. So let me show an example, actually, which I came across during one of our projects. So we had a really small data set, and our task was to predict the sentiment. So at the beginning, we had so because we had the number of sentences was relatively small, our model learned that word fine is positively correlated with positive sentiment, but obviously it suffered from this error, because once we get more data, we realized that due to especially stemming reasons, the word find might occur in this context. I was find, which sentiments is obviously low. So here you may see that at this point we suffer from this error. Here we realize this, and in the ideal world, we can actually assess this problem, because now we can discriminate between these two contexts, and we can build a classifier which actually is good for both of these examples. So, yeah, one may assume that once you get more data points, the epistemic error should decrease. But one shouldn't assume that it's possible to get the perfect data, because in theory we should wait, till the end of time. And one more interesting fact connected to this error. So this is not quotation actually, because here you should have quotation mark, but it's not displayed. So this is not quotation, this is actually the title of the paper, which was recently published, and it has a really ironic title. So do CFAR10 classifiers generalize to CFAR10? So this is, here you may see the author and the link to the paper. So what the authors of papers did is that they took the original CFAR10 test set, and they found really similar images. So here you may see you have a picture of the plane, and here you have a picture of different plane. So here you have a picture of the horse, and here, I guess you need to believe me, you have yet another picture of the horse. So it turned out that when they evaluated the state-of-the-art models on this new test set, they noticed that the accuracy severely dropped. So it's not that obvious when once you increase the number of data points in your data set, your model will be actually better. But this actually shows that CFAR10 is at this moment severely overfitted, in this sense that we know what models are good at this, and actually this was proven by the authors of this paper. Okay, the last type of error, which is really similar to the previous one, and actually in most of the classical sources you will read about only these two first kind of errors. The third one is, I think this is one of the novelty which came across in this paper, which I mentioned at the beginning. So this error is called out of the distribution error, and it claims that it's really similar. It also, so cases which suffer from this error are also underrepresented in our training data, but here you cannot expect that once you get more data points, you will have better model. So this is interesting because it's not in my opinion, this error comes not from the statistical properties of machine learning, but it comes rather from the way how we collect our data. So this is a purely technical error. It actually, it happens often when your training distribution, so the source of your data points for which you have the full knowledge, differs significantly from production distribution. distribution, so the points on which you deploy your model. So, where this error comes from? In my opinion, there are two main reasons why you can suffer from this problem. So the first problem, you don't understand the source of your data. So maybe I will come back to this later when I will tell about this example. And the second thing is that in many cases there is no practical way for collecting the full knowledge about new data points. So here you may see the example of the problem where which we solved at Sigmoidal, where we suffered from this issue. So we had a text classification problem. Our client was sending us labeled data and he asked us to train model on this. So we built a model, so this model was really easy and we achieved like astonished accuracy, astonished AUC, average precision, etc. And once we sent the results to client, he was surprised and he said that AI is overhyped because the model doesn't work at all. So we are really interested what happened. So we performed the following experiment. So we gathered a huge data set from him on which he ran our model. We represented this model by taking the mean embedding of text which he sent us. And then on our data, which he originally sent us, we trained PCA, and then we applied this PCA to the production data. And we noticed like a really interesting fact. So in case of PCA, you can also understand where the how the distribution differs. So it turned out that he thought that because this client works in the business domain, he thought that this is obvious that like articles which are not about the business will not be useful for us, and he didn't say us about it. So as you may see here, like the production distribution differs when it comes to the words like inflation, growth, economy, whereas the situation was similar here. So actually, no matter how long we will train our model, no matter how long we will wait for new data points from our client, these distributions, the training distribution and production distribution, were completely different. So we couldn't expect it. Okay, so I was trying to speed up. We couldn't expect our model to improve. Okay, so the trick for this is really it's the same. It's one trick to rule them all. So basically, as you remember, I mentioned that when you train your model when you want to decrease the entropy on this data set, one may assume that cases with low entropy are actually from our training set, or from our training distribution. So one can easily check whether the example comes from training distribution by checking the entropy. So I performed a really similar experiment. Now I took the test set from MNIST data set, and as the out of distribution set, I took the Fashion and NIST, which is pretty similar in terms of size and structure. And as you may see here, the entropy is, once again, entropy is lower for in distribution examples, and is higher for out of distribution examples. And it serves as pretty decent classifier when we want to discriminate between the in-domain and out-of-domain cases. So once again, by simply computing the entropy of the scores of your model, you can get a pretty decent model for assessing whether the case is from your distribution or not. The last thing, so one more minute. So the last thing are the next steps. So I showed you the simplest trick possible, in my opinion, by which you can assess the uncertainties. But obviously there are other relatively simple techniques. So first of all is like good ordered assembly. You always can train a set of models and check whether they agree or not. One may assume that they will agree on easy examples, and they should agree on examples from the training distribution, because only there they were trained to agree. Obviously, this comes at cost that you should have multiple models and should have multiple inferences. So one may ease that using some kind of Bayesian deep learning. All these three techniques are from the Bayesian deep learning technique. So one may train a single model and then obtain different samples of models using something which is called Monte Carlo variational dropout. In this case, you turn dropout on also during the inference phase. And these two techniques they're actually based on like corrupting weights by random noise, learnable random noise. And here in bias by backdrop paper you are simply adding the noise to the weights. And in this paper, multiplicative normalizing flow, you're multiplying your weights by random noise. That's all.
Thank you, Marcin. Any questions?
So I had a question, it's more of a general one. So all of those talks were actually about, accuracy, errors, which kind of, flims towards classification as a main problem of machine learning that we're trying to solve now. Within my research, I'm trying to kind of step outside of this problem. There's a bunch of reasons. One of them is, because big companies like NVIDIA would always kick me in the ass with a lot of resources that I have to be smart about when I'm trying to publish in my work, or whatever else for that reason. So my question is kind of an open one. How do you see this discussions around accuracy, errors, actually generalized for the problems that we're actually trying to solve with the quest that Kasper mentioned at the beginning, with artificial intelligence actually being able to be intelligent and not just solving benchmark data sets and kicking those records and MNIST and other data sets. So do you see actually this being applicable also to unsupervised learning or I don't know, other ways of machine learning?
So yeah, this is a really good point. So actually, I concentrated mostly on the classification error because, as you mentioned, it's like the most. So most of the methods are established for the classification. The second is regression, but it's also really hard for. So there are many different weird things which happens in the regression case. So in case of unsupervised learning, I think one may so actually there is a way how you can generalize the methods, and this is something on which I am currently working on. Because if you think about it closer, for example, in classification methods, especially when you think about Bayesian deep learning, you would like your models to behave the same no matter like the sampling, no matter different corruptions of your network. So in this sense, if in your unsupervised setup, you can provide some kind of measure whether networks behave, and so outputs or representations are pretty similar, no matter the sampling. This could be easily generalized, especially these Bayesian methods, which I covered only in original mentioned. But yeah, there is a possibility, but you're right, they are not widely explored.
Thanks, Marcin. Any more questions? Okay, so do you have, could you share some experience with using these other kinds of like dropout? Like you mentioned this kind of, I would call it like Gaussian dropout, right? So you're multiplying your weights by some random noise. So could you share some experience of yours? Like maybe why isn't it that much popular as this classical dropout, like Bernoulli dropout? Thank you.
So, well, the answer to your question is that because usually when you apply these techniques not to data, like the academic data sets, these methods don't work. And there are like so in my opinion, there are certain reasons, there are certain reasons, obviously I mean hard problems, because for easy problems, very often they work, but if this problem is easy, why one should bother? So the reason is that, so like my experience, why these methods are not so popular, is that in many cases, usually you want to apply them on the small data sets. And when you apply them to small data sets, usually like accidental structure of network may cause you, could make you a lot of problems. So this is something which we observed, that like in case of small data sets, you suffer from the inner network structure. This is also something which we suffered from in research in personal traffic, when we simply noticed that for some reason, like the fact that the rel function keeps going and going, this is completely changing your predictions. And this is something on which we have worked on, and actually we just submitted a paper to the CLR, which tries to deal with that. And my experience with this, in order how to deal with this problem, how to make these models applicable, is that we need to take into account the structure of the network. So for example, just to give you a brief example of what we did, we actually switched activations from the global one, like for example, rectified linear unit, which is global. If you learn it to behave in a certain way here, it will go to the infinity on the right, and it will be stay at 0 on the left. So it has global properties. So we actually use the kernel functions, and it worked really well. It helped a lot. So, but obviously you always need to find what actually caused the problem and tackle it. But from my experience, this is one of the most common one of the most common cases. Is the accidental structure of the network.
Thank you, Marcin. Do we have time for more questions? Kasper? I'm not certain this name. One more question. Okay, this is the last question. No more questions, right? Okay. If not, we can ask later Marcin during the after party. So let's thank once again to Marcin. Okay. So yeah, thank you Marcin once again. I would also like to thank once again to all our great speakers. And yeah, soon we'll start our after party, but before I invite you for the after party, I would like to give a few announcements. So, yeah, first of all, thank you also once again for your attention. It's great that you are here with us. We are not sure how many people will come because there were more than 130 people registered, and we accepted almost 100. And now we see that most of the people just came to join us today, so that's really great. So thank you. And I also know that most of you already joined our Facebook group. So if you haven't joined it, then please do it, because yeah, we'll be publishing some announcements in the future. For example, you just saw that we recorded our lectures. So these video recordings will be later published on our Facebook group, in social media. So we have a dedicated YouTube channel as well. And as Kasper said, we would like to build a great community of AI experts, AI specialists. And we would like you to help us. So if you have any feedback, what we can do, how we can improve, then feel free to send us email. Yeah, we can use one of these two email addresses. And just let's stay in touch. So give us feedback. And Warsaw.ai will strike back in the future. 3 months from now, there will be episode 2. On 17 January 2019. So we are not sure regarding the location. Maybe it will be also here, maybe in another location. We'll see. So we invite you now already. So just yeah, we'll let you know later about date and location. But there are also some other interesting events. We are befriended with a few other meetups and interesting groups here at this university, at this faculty. So, for example, we have machine learning student group. So Mateusz Macias is leader of this group, and he's doing. It will change, yes. So the date will change, yes. So where will be the first meeting?
I'm not sure. Most probably it will be Monday.
Monday, but not next week yet.
Not next week.
Okay, so There's also a Facebook group of this machine learning association, so also, yeah, just feel free to join this group, and Mateusz is doing a great job leading this group. Another interesting event is Polish View on Machine Learning. So it will be a very good conference in December. Also, this faculty, I know there are also a few organizers of this conference. It's Agnieszka here, yes, it's here. So I know that it's still possible to apply, right? And register and also submit proposal for a talk and post, right? Okay, great. Okay, so the next meetup is Warsaw Quantum Computing Group. So it's a new initiative. In this case, I'm a project leader, and we would like to start on 12th of November. So as some of you maybe know already, quantum computing is also expected to enhance artificial intelligence in the futures, and there are already many quite good algorithms which are ready and are expected to improve AI again. Real quantum computers in large scale are not ready yet, unfortunately, but there are already some programming languages and programming frameworks released by Microsoft, IBM, or Rigetti, and you would like to learn how to write code which can be run on these quantum computers, how to develop algorithms which can enhance artificial intelligence. There are already researchers on this planet who work on such algorithms and publish very good papers, and we would also like to invite such people. So I also invite you to join our first meeting that will be on 12th November, also in this faculty, and maybe even also in this room, learn together with us how to implement AI on quantum computers in the future. And now, thank you once again for your attention. It's time to after party. Thank you.